workshop aiming to present the results and the outcomes of the projects selected during the first FF4EuroHPC open call. So today's workshop includes experiments related to maintenance, agri-food, and asset management. So we will start by an introduction to FF4EuroHPC, which will be done by my colleague Tina. Then the first presentation will concern AI ML computer vision for the next generation and farms by Tomo Popovic from DigitalSmart. The second presentation is dealing with massively parallel power network simulations and optimization, and which will be done by Jean-Luc Bouchot from Artelys. And the last presentation will be done will concern Axyon AI leveraging HPC for AI and DL powered solutions for asset management, and will be done by Giacomo Barigazzi. We will end this workshop by some conclusions and wrap up. So a session of 5 minutes for questions and answers is planned at the end of each presentation. So please shake your hand, or if you have question, or you can ask your question in the question section, or send your question by chat. Good. I let the floor now to my colleague Tina to introduce FF4EuroHPC project. Please, Tina.
Hey, good morning. So I hope now you can see the screen.
Yes.
Yeah, perfect. Good morning from my side. My name is Tina Martz, and I'm a FF4EuroHPC communication lead. And today I will just give you a short introduction to the project and give actually the context of the success stories that will be presented later. So FF4EuroHPC is a H2020 research project. It is coordinated by HLRS, and then 5 other partners are contributing to the project. This is Arctur, Sesga, Chinekas, Kapos, and Teratech. So actually FF4EuroHPC connects business to the cutting-edge technologies. Our aim is to increase the innovation potential of industry, and we are focusing mainly on the SMEs and promoting them the use of HPC and other technologies such as AI, machine learning, HPDA, and other technologies to introduce them into their business and become more innovative and thus more competitive. We actually also connect SMEs to the national competence centers and digital innovation hubs, which then promote the services and allow or offer the HPC infrastructure to the SMEs for their further use. We also would like to encourage SMEs widely to use those technologies for their business and thus foster wider innovation. And this is not only by offering the open calls and giving the opportunity to SMEs to actually apply and get some funding to get involved into their further experiments, but also by promoting best use cases from the actual application of technologies in their business. And lastly, we are actually promoting the open calls to the SMEs, and in this way we are somehow offer the inclusion of SMEs to lower their barriers to the market, and finally introduce them infrastructure to build new business models and new opportunities. So I mentioned that we offered 2 open calls through this project, and in this open call we were targeting the high quality experiments from innovative and agile SMEs. So in total we got 42 experiments that were selected through the evaluation process and funded. And they are including 132 partners from 22 EuroHPC member states. And if we can see the picture of the map, the dark colored countries actually at least one partner is from those countries is involved into this project, and we are really happy to cover this wide geographical area. I would like also to mention that 62% of our partners are actually SMEs, and they are addressing different business challenges from various industrial domains, but mainly we are focusing on manufacturing, where we got 57% of all experiments, but we are also covering other industrial areas from automotive, manufacturing, I also mentioned, so healthcare, agriculture, and some other sectors. So how do we get the success story? So partners somehow collect different contributors. So we have end user, we have HPC provider, and then technology or domain experts. Also, ISV could contribute to the experiment. They are building the consortia, getting the business challenge that needs to be addressed by some technology, and then the experiment is running for about 15 months. And as soon as it is successfully concluded, then we got the success story, which highlights the business benefits, and through this story we are inspiring the industrial community. At the moment, you can visit our website where you can get the description of all 42 experiments which are addressing business challenges from various European countries and various industrial domains. And at this point, I would also like to invite you to visit the website, also our social media. When we are promoting the success stories, we are also communicating HPC relevant events and HPC related content. I also like to mention that all these 4 webinars we were holding in the last 2 months will be also offered on our YouTube channel, so you can get the chance to have a look at the success story presentations. So this would be all from my side. Thank you very much, and I wish you a nice enjoying your presentation.
Then we should get started.
Yes,
I'm going to talk about massively parallel power network simulation and optimization. And that's part of the SciMap project, which is Power System Maintenance Planning for the Energy Transition. So this is probably a slide some of you have seen in past presentation, but let's recall a little bit. That's a collaboration between Artelys. So Artelys is a French software company specializing in energy and numerical mathematical optimization, a bit of mathematical modeling, and but we specialize a lot in power network system, and recently we've moved towards data sciences and all this kind of thing. So basically, wherever optimization is needed, we try to show some expertise in it. And we collaborated with the INRIA, especially the AVIS team. So for those of you who are not in France, INRIA is a big research institution, mainly specializing in computer science and automation. And the AVIS team is specializing specifically in massive unstructured data. And so we'll be working with them in order to basically evaluate and visualize the results that we get through the these massive simulations. And of course, that through FF4EuroHPC, which has been introduced. So let's not talk about that again. So we have a general problem. The general problem is we have different levels of power generation. So on the top part, we have very high voltage, very high capacity power generation. So nuclear power plants, coal plants, hydroelectric plants, etc., etc. And as we go deeper, we go roughly into lower voltages. And at the end of the pyramid, basically you have the consumers that you see on the left part of the graphs there. And then on the right part of the graph, you'll have all sorts of smaller generations, you know, wind and solar panels being one of them. And we also have, because we're looking at a power network, but a European-wide, we also have all sorts of transmission. So basically transmission between France and the UK, transmission within the North Sea and all sorts. And it's quite important, especially in the high volatility of the market, to understand how electricity is exchanged between partners and what needs to be done whenever we are trying to shut down an asset. I'll talk about that in a minute. So what we have today is we have a part that is weather dependent. So basically the hydroelectric power plants, as well as solar and wind power plants, are very dependent on the weather. So if it doesn't rain enough, we will not have enough water in the hydroelectric power plants, which means we do not have enough control on it if it hasn't rained enough and all these kind of things. So we have dwarfed and we don't have any power there. We have things that are intermittent and cyclic. So precisely, solar panels can be very good. However, there is very little chance you'll get any power out of it between, say, midnight and 6 a.m. And we also have the intermittence in terms of wind. So if you have enough wind farms, you may get some powers more or less continuously, but it's still a rather dangerous bet. And then, of course, you have some limitation in the green part. If it hasn't rained enough, then you have little control on it and everything. And we have a lot of what-if problems. So typically, power plants need to be maintained regularly. So if it's a nuclear power plant, you still need to refuel every now and then, or even just have a bit of a maintenance for just regular reasons, basically. You also have some interesting things recently. So we're trying to include more and more electric mobility, and that obviously is still something we don't know exactly the impact. We have storage, which is in the beginning a little bit of all the it's just starting at the moment, and it's not really well understood and well deployed, I would say. So if you want to know, at the bottom right part here, you have the Trafford Energy Storage, so that's near Manchester. And you also have heat networks that you can try to include, and all these kind of things. So basically, that's a lot of things that interact with one another. And our goal here is to find a maintenance plan. So basically, given a set of assets, we are trying to find when is the good time to put the maintenance on them. And the maintenance means shutting it down, but then refueling or just repairing what needs to be repaired or whatever. So whatever the maintenance is for that thing. And we want this solution to be robust against CO2 emission, loss of loads. In other words, whenever the demand is not satisfied. Well, you also want to not waste anything. Basically, you don't want to overproduce, otherwise the energy will just go to waste. And all this you want to do by reducing the costs also, because at higher costs, obviously, then the consumer, the customer, will eventually pay the price. And as I said, we have a lot of uncertainty. We have uncertainty in the climate data. We have uncertainty also in other assets. So let's say I want to plan a maintenance on a certain specific asset. There could be the case where another power line or another asset just failed at that time, at the time that I had planned. Typically, there was a fire between the French and the British transmission line just a year ago. And that has an impact also on the network, obviously, because then there was no transit here, or very little transit, power transit there. And if you decided to put a maintenance of a big asset at that time, then obviously you can't count on this flow of power, of energy there. And of course, then we want the demand to be satisfied at all time. I'm not going to go, that's probably the one mathematical slide of the presentation, but basically what we're trying to do is we try to minimize the social welfare, minimize the costs, and we have a little bit of the omega here to describe the uncertainty that we try to embed. M will correspond to the maintenance plan, P to the production plan, and of course the production plan says that everything that is being produced somewhere has to be consumed elsewhere, and that's what we try to say with the Kirchhoff flow. And basically, if you have just a power line, then you produce on one side and you consume on the other. And at the other node, you produce and you consume, and so on and so forth. So basically, if you think of it as a graph in mathematical terms, you'd probably have always consumption, generation, But that's just a technical part that you don't need to understand. Basically, what we want is that everything that's produced is consumed, and all the expectation of the consumption is produced. In other words, demand is satisfied, we don't produce too much, and we don't demand is satisfied and we don't produce too much. So as I said, we have maintenance plan and production plan, and want to optimize both of them. And what we'll do, we'll have we'll be going back and forth between optimizing the maintenance plan and then production plan. So in other words, I'll suggest a maintenance plan, and with this maintenance plan, I will optimize the production plan. And then with the knowledge of the cost or the empirical risk on that maintenance plan, I will re-evaluate it and then suggest a new maintenance plan, re-evaluate the production plan, evaluate its cost, and so on and so forth. And that's what I try to summarize here. So basically, we have some input data, and the input data will be, roughly speaking, the historical climate data. So we have about 30 years of climate data that we have analyzed, modeled, and modeled their impact on the production of electricity. We also have, so once we have that, we'll generate some outages, we'll generate some kind of stochastic perturbation of these plans. And then once we have that, we pass it into the maintenance planning optimization. In other words, what we'll do, we'll be looping. So suggest one maintenance plan, and then figure out what is the cost of this optimization plan, and then re-evaluate it, or suggest a new optimization plan, and then re-evaluate its cost, etc., etc. And that's what we do. So through the maintenance planning blue box here, we basically adapt our expectation or change a little bit. So let's say if we decided to have a maintenance plan at week 2, then we'll shift it to week 4. And then afterwards, the green box, this is where we have massively parallel HPC simulation. So we'll take all the climate data we have, all the stochasticity uncertainties that we have, we'll cross these scenarios, and then we'll send this to an HPC. All these scenarios will be evaluated. So let's say I want to evaluate the maintenance plan that I think would be good at week 4, and I will evaluate it against climate data from 1990 with an outage on the power line between France and the UK. And then I'll have another scenario, which will be the same maintenance plan, but an outage in a certain power plant in Estonia, for instance, and so on and so forth. I'll have thousands of such scenarios. I'll simulate all of them. All of them will give me a production plan, and then I'll basically mix all these things, and that's that little yellow arrow going back up into the maintenance planning box. And then basically all these scenarios will give me some information about whether this is a good plan or not. And if not, then I can reevaluate. So for those of you doing a bit of optimization, I'll have some kind of local heuristic to help me understand what would be a good update on the optimization plan. On the maintenance plan, sorry. And then once we have reached the end of our loops here, and that end of loop could be either my algorithm has converged, or it could also be I have exhausted all possibilities. Then I'll just post-process the scenarios and try to visualize them, and then make a good decision based on that. Let's have a little bit of numbers. So we have, as I said, 30 years of climate data, so including wind, solar generation, and also some things there, with the power grid as we know it today. So basically, we took the climate data and then modeled what would happen or how much power would be generated today if we were to have the climate from 1982 to 2011. We have generated also some likely outages on other production assets. So let's say, as I said, a coal power plant somewhere that is being shut down randomly for a fire or anything. And this is, let's say, 30 to 50 random scenarios that we will mix. So basically these outages, these uncertainties will be mixed with the 30 scenarios that we get. So that's roughly 900 to 1500 scenarios that we have to simulate at every iteration. And this is for 30 countries, and because that's the European-wide network, and every country has roughly 30 assets. So we've clustered them together. I'm not going to go into details, but basically we have about 900 power assets that we need to, for which we need to optimize the power generation overall on, let's say, roughly 1,000 scenarios. So that's a massive problem, really. I'll go into more numbers later, but just to give you a bit of an example of the kind of things that we get, this is basically the Austrian and French climate data 2009, and this is the demand that is needed for these years according to the models that we've developed. So basically that takes into account the wind, the temperature, and the fact that we have a bit of a heating system and blah, blah, blah. So all these kind of things that we've modeled together, and that's what we expect the power demand to be in today's characteristics of the world using the climate of 2009. And you'll see you'll have some, kind of cyclic things that are happening over weekends and these kind of things. If you're interested in that, there's a lot of data science to be done there. In terms of HPC, so the input data, depending on the types of scenarios that you consider. So as of right now, we're working with XML files, which we know is not ideal, but we're working on improving this. But that's roughly, let's say, 10 to 100 megabytes per file. And that means one input data needs to be duplicated 1,000 times at every iteration. So that's 1,000 times 100 megabytes. I'll let you do the computation on that. And then the way we generate these XML files is just a small JSON file and a little config file. So that doesn't count into nothing. But the output data is roughly 10 times bigger than the input data. Again, so that's roughly 100 to 1,000 megabytes. Again, times 1,000 scenarios per iteration, and then some iterations over that. And as I said, we have roughly 30 times 50 or 30 times 30 scenarios. So that's roughly 1,000 to 1,500 simulation per iteration. So that means roughly 3/4 of a terabyte per iteration. So that's a massive amount of data that we get, especially we get a lot of iterations if the optimization is difficult. So we expect, still need to run a few tests there, but we expect about 50 iterations to reach a nice result. But this will, of course, depend on the problem we have, on the dimensionality of the problem, and so on and so forth. So it's hard to give a proper number on that. In terms of computing, so that was all storage thing. In terms of computing, really, we have one simulation lasts about 2 hours. So if you count 1,500 simulations, that's roughly 125 days of computation per iteration. We also have the issue of memory, and on the scenarios that we had roughly 20 gigabytes. Oops, sorry, 20 gigabytes of RAM per simulation. So which means, at least on my laptop here, that wouldn't work. On my personal laptop, might have a chance to make it work, but we probably not want to let it run for 125 days just to simulate climate weather. And on the cluster that we had, that was roughly 40 nodes. We have it multi-threaded. I wrote 250. I need to check. I think it's probably 200 gigabytes of memory per node. Might be wrong on that one, but and then that means one iteration lasts just a few hours. So we went through this HPC usage from 125 days of computation per iteration to a few hours really, let's say 5, 8. And overall, if you want to optimize, then of course, depending on the number of iterations you have, this is just a handful of days. And in some result, that will look very much similar to what we had before. So I'm taking same countries, Austria, France, same climate data, 2009. And here I have no outages. It's just purely the climate data in today's topology of the network. And then you see we can split basically the various productions. And you'll see that you do not have any nuclear power plants in Austria. We have a lot in France. Yeah, let you decide whether that's a good thing or not. But obviously, then you have to account for other production. Red being OCGT, so open circuit gas turbine, so basically resorting to gas. And that would be, for instance, interesting to see what's going to happen now, because this was as we knew it, and gas might not be there tomorrow. Well, so all things will change eventually. And I must admit that was not an uncertainty we had planned when we started that. And if you're interested, of course, because this is a very, very generic software that we've developed through this project, but it's very generic. So if you're interested in renewable energy, we could also just try to emphasize the visualization on renewable energies. And here you'll have only hydro power plants, solar fleet, and wind. And I wrote only offshore and onshore here. I mean, Austria doesn't have any offshore. Guess what? Guess why? But yeah, but this here has changed from the previous slides where it's all scenarios. I've basically mixed up all the scenarios that we generated into one single view. So there is a good thing out of that, a very, very good thing, I would say. So we did something very generic. The goal was to have a bit of an optimization for the maintenance plan, but we've managed to keep the optimizer. So the first blue box in my loop that I showed earlier, fairly generic, which means it is applicable to many solutions. We were lucky enough that some colleagues had to work on what's called the PEPS-5 study, which is a study interested in the impact of storage in the future. And so that's not an optimization problem per se, but it's the generation and simulation of many potential scenarios. And then afterwards, there is a bit of an analysis through the optimization expert that's being done. Now, we were happy we could help them. So basically, through the software that we developed in this project, we were able to adapt a little bit our optimizer and to basically change it into a brute force or an exhaustive optimizer, if you wish. And that allowed us to basically generate and monitor and visualize all the scenarios with very little human interaction or human involvement in the process. So that saved us. I don't know how to quantify this precisely, so this will be hand-waving estimates, but probably a couple of weeks worth of work just by doing that. This is a very important study. The customers of that were, I believe, the ADEME, so that's the French Agency for the Ecological Transition. Well, probably not the customer, but they were in partnership with that, so to finance that somehow. And the Association for the Environment and the Energy. See, these are two big players in the French renewable energy ecosystem. All this was also about long-term scenarios, so that has something important. And one last part, which is very, very important in the visualization, is we have, as I said, gigabytes and gigabytes of output data in there, and of course, visualizing all this is very difficult, and that's why we had to resort into computing KPIs, which were computing asynchronously, and that's again a few hundreds megabytes per KPI of KPI alone. So that's still a massive amount of data, even though we reduced them. And these KPIs are cost and how many times we have missed the demand over a scenario and these kind of things. And that's also something we developed that we were probably not expecting a little bit, hoping for anyway, but we weren't sure we'd have time to do this. But so this came out of the study also. We had to push a bit forward the KPI implementations and development and all this. On this note, I want to thank a lot for the funding. So that really helped us a lot. It developed. We've managed to get software that was ready enough to be used in a study within a year worth of time, and I don't think that would have been possible without this funding. So I want to thank a lot everyone in this joint initiative for this opportunity. And of course, if there are any questions, I'm happy to answer them.
First, thank you for the opportunity to present our experiment and our project and this workshop. And the title of the project or experiment was AI ML computer vision for next generation poultry farms. Next slide, please. So the outline will follow the proposed outline that you send us in templates. We'll discuss briefly the objectives, motivation, then the challenges, solution, main outcomes, and the impact of the solution. Next slide, please. So just briefly to mention the companies or the partners involved. So we have a DigitalSmart, that was a technology expert, relatively new company registered in Montenegro. Then we have a Dunavnet company that had the role of independent software vendor who is offering IoT solutions for smart farming. And then we have University of Donja Gorica, who is also implementing a National Competence Center through EuroHPC project. And their role was to provide HPC expertise. And then we had two end users, Mesopromet Franca and Radinovic company, both from Montenegro. As for the HPC center, we use the services from a company from Croatia called Jota Advanced Computing. Next slide, please. So as far as the objectives and motivation, we have these general, world problems of growing demand for food and growing demand from protein. And we were thinking how to, provide support for all that, and how do we scale and optimize farming process and poultry farming process, if you will. And can we use artificial intelligence, machine learning, and HPC to contribute to solution to this problem, at least partially? And can we do it by limiting the effects to the environment and also, improving the well-being of animals? So this is kind of the motivation behind this work in general, not just this experiment, but this experiment is part of the equation. Next slide, please. Now, the focus that we had here is if we started from a relatively state-of-the-art Internet of Things-based solution for digital farming, namely for poultry farms, can we improve these solutions and sensors by adding smarter sensors, computer vision sensors that will provide us some additional functions that are not just measuring some typical environmental parameters in a farm. For example, things that come to mind is detection of dead chickens or detection of dead animals. Also, can we, for example, follow the progress or make an assessment or identify some problems in the growth of or weight of animals during the cycle of their the farming? So can we move to the next slide, please? So what well, this is kind of the approach, how we organize the experiment. We first, had these tasks of defining and identifying requirements. Some of that was done prior to the experiment. Some of that was done during the experiment. And then we were focusing on development of prediction models using HPC and prediction models that we wanted to identify and develop were related to detection of or early detection of the problems with animals or early detection of disease, namely the detection of animals that are not moving or potentially dead animals, or if we could identify certain issues in their size. After we developed the prediction models, the idea was to experiment and test the proof of concept with integrating these prediction models into the edge devices or edge AI devices, meaning like smaller devices capable of running these prediction models directly in the farm and then sending the information that's extracted from the images collected in the farm in order to provide enhanced decision support system for the farm. And finally, the task, the experiment involved validation and interaction with end users. And also throughout the project, we had several activities related to project management, dissemination, and exploitation. So next slide, please. So the approach for the solution is to use deep learning and to utilize HPC in order to develop good prediction models, and also to create models that we are able to port onto the edge devices. So next slide. Once we kind of have these prediction models on these edge devices, you can consider them being intelligent sensors or sensors equipped with cameras, but that they act as a sensors for detection of chickens or detection the size of the chicken. And then we needed to integrate these sensors with the existing digital farming platform that was provided by DunamNet, and possibly enhance the decision support system, and at least show directions how additionally can these digital farming platforms be improved using a sensor, these new types of sensors that we developed. Of course, the target is to lower the cost of labor and also to increase the productivity by preventing spreading of diseases. So can we move to the next slide, please? We focused on the analysis of requirements. Basically told us that we need to focus on two types of prediction models that we have to develop. One is for detection of chickens that can be used for both counting chickens in the image or detection of chickens that are not moving or potentially are deceased. And also to do a segmentation of chickens in the images in order to be able to assess the size of these chickens. So we were focusing on two artificial intelligence or machine learning types of models that we need to develop that would later on help us develop new functions for the platform based on this additional information. Can we move to the next slide? The idea is to create the computer vision machine learning edge kits for poultry farms. So these kits would consist of edge device. In our case, we experimented with NVIDIA Jetson cards, but it could be different cards that have a capability of running these prediction models. Connect them to a camera, and then perform the execution of these prediction models on the device itself, and send the extracted information back to the platform in order to enhance the decision support. So one part was integration with these edge AI platforms. The other one was integration with the digital platform in order to improve its functionality. Our focus was on benefit to add functionalities such as counting of chickens in image, detection of dead animals, and assessment of growth. So can we move to the next slide, please? So in order to do this, we needed to have a data set. We kind of dealt with the data set that DunamNet came with. It was an initial data set of a few thousand of images. Then we also installed these edge devices on the end user's platform, and we collected additional a few thousands of images, and we needed to perform annotation of these images in the data set in order to make them ready for training the models for object detection and object segmentations. Object segmentation annotation was much harder because it required basically to draw manually a polygon around every single chicken instance, but we managed to have around 1,000 images of those as well, and then we had around 6,000 images for object detection. Additionally, we use some tools to perform augmentation on images in order to, such as rotation and similar, in order to extend and expand the data set we worked with. So next slide, please. So then the focus was to utilize HPC to train the models for both object detection and object segmentations, as we'll see on the next slide. We basically experimented with different architectures. For object detection, they were based on faster RCNN architecture, but we experimented with different architectures in order to perform some sort of brute force or grid search to find which architecture would give us the best results. And then once we detected the specific architecture that had the most promising results, we continue experimenting with this particular architecture and with fine parameter tuning in order to achieve the best results. We also tried different HPC configurations, such as number of GPUs and number of CPUs, etc. Next slide, please. So similarly with segmentation, we experimented with mask-R CNN architectures, and then we selected the one that was giving the most promising results, and then we were playing with parameters and searching the best parameters for the images that we had in order to get the best results. Next slide. So the main outcomes come to the selection. This experiment, you know, helped us out to save time and identify the most promising architectures for these training models. And then further on, we ported those models onto the IoT platform. And we also managed to integrate the information collected from these sensors or new computer vision sensors with the PoultryNet commercial platforms. And we were able also to validate the functionality with the images collected from the end users. Can we move to the next slide, please? So, as for the business impact, I think it was very critical for us, being technology SMEs, both DigitalSmart and DunamNet, that HPC and access to funding from this project help us to speed up the innovation, you know, and increase the innovation potential of our companies. We were also able to get to the position that there is an enhanced platform for smart agriculture, in this case, poultry farm. PoultryNet is the name of the platform that can, again, provide benefits for agri-food sectors, which are also often SMEs. For us as technological companies, the time savings was critical, and it is we had a twofold benefits there, in the sense that use of HPC enable us to locate particular architectures that were promising, and then to tune the parameters and customize the prediction models based on the images for particular end users. They can also, there is also a promise that for the next end user, we might be able to do this customization much quicker than before. Can we move to the next slide, please? I would just remind you that the focus was to develop sensors that will allow us to develop solutions for early disease detection and preventing the disease spreading among the animals. This is where having this sensor in place is really beneficial for the end users, because quicker you get the information that something may be wrong and quicker you react, you might be able to dramatically improve the productivity and yield that you have, but also well-being of animals if we prevent the spreading of the disease earlier. Next slide, please. So the summary of these, I mean the overall benefits is that we are hoping to improve the animal well-being while achieving better product quality and better yield of the quality. Also, as far as the environmental impacts, we expect to have a better management of dead animals disposal, early, detection of dead animals, and possibly lower greenhouse gas emissions. Also, the great improvement on time savings for us being the developers, definitely more than 10 times for development and customizations of prediction models and development of custom calibrated sensors for specific end users. The accuracy that we achieved in this experiment was over 90% for prediction models, both for chicken detection and chicken segmentations, which can again lead to much quicker identification of some abnormalities or possibly early detection of diseases. Again, we might be talking about seconds for the camera and prediction model to react, and maybe minutes, to send some alerts to the users, which could be compared to hours or in some situations days for them to manually, detect these possible problems. Again, partners on this consortium expect 10% reduction on both of the level of manual labor costs, and more importantly, 10% reduction of the chicken mortality rate, which is probably where the money benefits for the end users will come from. Next slide. I also wanted to mention that we had a collaboration with the newly established National Competence Center of Montenegro that is being implemented through EuroCC project, and they provided us with the help in providing some expertise in HPC, but also I think there was a great help there from UDG and NCC with respect to dissemination, organizing events, exploitation, contacting possible other end users, etc. So I think this was really worth mentioning here. Next slide. As for dissemination, we had at least 8 presentations, and then we participated in at least 3 roundtables. We had one conference paper that was presented at the IEEE conference in Barcelona. We have one journal paper that is in preparation. We also created a promo video that we used for promotion both on these events and on the social media. We had several social media and website posts. As for exploitation, we worked with you guys on making a lean canvas. And then we also worked with DunamNet and DigitalSmart to integrate this with the commercial platform PoultryNet and basically use it as a framework to offer this as a commercial service to existing customers DunamNet has, and also through their channels for the distribution network that is already established. Next slide. Yes, and I also wanted to thank you in my personal, behalf and also in behalf of the whole consortium. We really think that this funding and this project helped us out much quicker work on some ideas that we had and discussed before, but we were not able to do without this support. So thank you very much.
So our goal for this experiment was to leverage HPC to build a AI and deep learning powered solution for the asset management industry. We had 3 partners in this experiment, ourselves as the end user, the University of Modena and Reggio Emilia, and especially the AI Image Research Center of the Software Engineering Department, and Cineca as the provider of the HPC infrastructure. Some information about ourselves. So we are a startup based in Italy, and we started our company in 2016. We were part of the acceleration program run by ING Bank in the Netherlands. And after participating in this program, we raised funds from ING Bank in 2017, and then another round in 2018 from ING again and UniCredit. And this allowed us to build the proprietary machine learning platform that is the basis of our company, that we use internally to build the machine learning models that then are used by our customers to improve the performance of the investment strategies that they manage. Since the very beginning of our company, we had a tight collaboration with the University of Modena. They provide us with the academic expertise and know-how that is necessary for us to stay on the edge of the technology in terms of the deep learning models that we use to build our algorithms. And then Cineca, of course. So what we do is basically using many data coming from the financial data providers such as Refinitiv, MSCI, FactSet, and train models to build some of the components or the complete investment strategies that then we provide to our customers. One thing that I really want to focus on is the fact that the asset management industry is an industry that is always changing. Financial markets are an always changing environment where new data is available every day, every second actually, or millisecond, if you work in the high frequency trading. And the important thing to notice here is that it's a learning game. So while in other industries, it's possible to reach like 99.9% of model performance in identifying, I don't know, distinguishing between cats and dogs, the typical example. Once you train a model that is able to do so, then probably this model will be accurate enough for the next for the next few thousand years. In the asset management industry, things change very frequently, and for this reason, it's crucial to build a factory of predictive models that are able to leverage the new technologies, and this is part of the game. So it's important to notice that the model retraining, once new data is available, when there are huge events worldwide, it's necessary to retrain the models and make sure to incorporate I mean, what happened in the world that could affect the financial market industry. We, as a company, what we do is, as I said, helping asset managers, but in the asset management industry, we specifically target the active asset management sector, which is facing a fierce competition by passive and alternative funds in the last few years. So it's clear that in order for active asset managers to bring value to their customers, it's really crucial for them to be able to deliver alpha, which means outperforming the average performance of a specific index or of a specific asset pool. And artificial intelligence, machine learning, and deep learning have already reshaped many industries, but in the asset management, this is something that is taking a bit more than in other segments. But now it's clear that for every player active in this segment, it's crucial for them to be able to leverage the AI and deep learning predictive capabilities in order to stay in the market and be competitive. For us to deliver value to our customer, we have a solution which is called Axyon Iris. It's a suite of AI solution for asset management, where we provide AI-powered investment strategies and end-to-end strategies, if the customer wants this. We provide also some of the components of the investment strategies, such as asset performance rankings and other information that are helpful to create an investment strategy that is able to outperform the market. We do this by leveraging an hybrid high performance computing and cloud infrastructure, especially the highest perform HPC infrastructure is used for the model training phase. Then for the inference, as we are not working in a high frequency trading, there is not so much need for a specific infrastructure, but for the model training, and as I said before, as it is necessary to train and retrain the model relatively often, the HPC capabilities are really fundamental for us. The specific goal of the experiment was to build and release a better version of our Axyon Iris product, and we focused on three main areas. First, scalability, second, risk management, and third, the AI adaptiveness of our models. As we were three partners, we decided to, let's say, divide also the activity with respect to which partner was most involved in each of the tasks of the experiment, with, of course, ourselves being involved in all three. Cineka was a lot involved in the first task, the scalability. With respect to the risk management, that was something that we did mostly with our internal resources, and the AI adaptiveness of the models was something that was done especially with the collaboration of the University of Modena. With respect to the first task, scalability, the goal was being able to train models with a larger number of input data and with a larger number of targets. In the asset management industry, probably I don't know if everyone knows, but basically when you build an investment strategy, at the very beginning, you decide which financial instruments you want to focus on. So you decide the size of the asset pool. And in our case, before this experiment, we were not able to train models that were targeting more than 100, approximately 100 of financial instruments. And this was limiting us in terms of dissemination activities and the opportunity to target customers that were interested in larger asset pools. So the first goal was being able to expand the number of assets included in the investment strategy. The second task was most devoted to improve the risk management process of the investment strategy. As you know, in the asset management industry, what you want to do in very simple terms is maximizing the return of the investment strategy and minimizing the risk. For the first years, we were more focused on increasing the return, but we were not really working enough on the risk management side of the investment strategy. So what we did was leveraging AI and deep learning and build models that were especially targeting the risk management purposes of the investment strategy. And this allowed us to being able to deliver to our customers an end-to-end portfolio construction and management system. So as I said before, first years we were more focusing on increasing the return. Now the goal was decreasing the volatility, meaning decreasing the risk of the investment strategy, And as these are the two main components of the investment strategy, we are now able to deliver an end-to-end solution to our customers. Lastly, the AI adaptiveness of the models. So as I said at the beginning, the need for model retraining is something that is especially necessary and important in when you want to build a predictive model for a sector that is changing a lot and very frequently. So being able to adapt the models and retrain the models minimizing the cost is really important. Otherwise, the cost for us to maintain an investment strategy and thus the cost that the customer pays would be too high, especially for serving asset manager and hedge funds that are relatively small with respect to others. So what we did was improving the robustness of the model retraining process by implementing continual learning solutions that prove to be a great way to decrease the cost and improve the performance of the models once they are retrained. The two main somehow components that contributed to all the three tasks were the availability of data and infrastructure. So we had to select the input data that we needed to use to train the models. These data are both the typical financial data, prices and volumes of financial instruments traded in the markets, but also context data that could provide to our models a more general overview of what is happening also on a macroeconomic level, for example, or other sources of information like weather forecasts that have a huge impact on the commodity prices. And of course the infrastructure. So in order for us to train models with larger data sets as input, it's necessary to have the HPC infrastructure and also the capability needed to train models on HPC infrastructures. And that was something that we focused a lot with Cineca in along all the experiment. And then the second component that allowed us to work on the three tasks that I was describing before was the combination of a highly efficient and rigorous process that we have designed to manage the model training of financial time series. Our platform has been built over the last few years, especially to train models over financial time series data, and that's the main. These are the main data sources that we have, and it's important to notice that for this kind of data, there are typical problems and biases that all quantitative models face. Overfitting, data leakage, human bias. These are a few examples of what we needed to solve by combining like a sort of model factory to build the models. So the solution was basically to build and improve the model factory that we use to train the models for asset management. We were able to boost the computational scalability of our platform, reaching investment strategies that included 1,000 financial instruments instead of 100 financial instruments. And that was something that that was a crucial goal for us. And lastly, as I said before, the adaptiveness of the models. So we implemented some continual learning techniques to increase the adaptiveness of the model and to reduce the time needed for model retraining, allowing us to retrain the models more often. And also, and that was something that we did in the dissemination activities. This led this continual learning activities that we have performed allowed us to present the results of this research in a couple of conferences and discovering, among other things, that not all continual learning techniques are best for handling financial time series data. In terms of outcomes and impacts of the solutions that we have developed, in terms of computational scalability, we were able to save costs. So approximately a 25% cost saving. I mean, all other things equal, and this allowed us to save money. And also to expand the number of financial instruments that we were able to include. The larger financial instruments of the investment strategies, in addition to the better risk management feature for end-to-end portfolio constructions, allowed us to expand the target market. Approximately, we have expanded by 150% the serviceable obtainable market. So now we are able to work with smaller financial institutions with respect to what we were able to do before, as we can provide a full finished end-to-end portfolio construction and management solution to a larger number of customers, considering that smaller financial institutions that were not the target of our sales activity at the beginning can now use our product. And lastly, and this is I mean, that was the main result of the continual learning activities and research that we have done. We were able to decrease by 30% the time needed for model retraining, and in addition to this, we were able to improve the model performance, thus the performance of the investment strategy that is powered by our algorithms. Well, that was it. Thank you very much for your attention, and I'm very happy to answer questions in case you have.